In the days leading up to a quarterly earnings report, the most valuable data in the world is physical. If an investor can track the volume of freight moving in and out of a competitor's distribution center, they can build an independent revenue forecast before the market reacts. Building that forecast requires monitoring the velocity of heavy transport logistics moving along dedicated industrial corridors. But there is a physical limitation to consider. At a resolution of 10 meters, a 20-meter truck disappears entirely into two solid, low-resolution pixel blocks. At this scale, you cannot count the vehicles. Instead, the target is a specific blue, green, and red spectral smear spanning 3 to 5 pixels across the highway. This anomaly occurs because the Sentinel-2 satellite does not capture all colors simultaneously. It records red, green, and blue light roughly 1.01 seconds apart. For an object moving at highway speeds, that interval creates a physical separation of the color bands in the final image. Exploiting this temporal offset once required massive institutional capital. Today, an independent actor can execute the exact same mathematical extraction for less than $100. The barrier to entry for planetary intelligence has moved from the size of a capital budget to the precision of a technical workflow. Historically, the procurement of satellite imagery was a manual, restrictive process. Enterprise licensing and massive minimum order areas meant that small firms were priced out of the market entirely. Market reforms in 2026 have replaced that bottleneck with transparent, API-first marketplaces. Platforms like UP42 and Skyfi allow users to define exact bounding boxes and pay only for the data they need. This shift has collapsed minimum order sizes. Where sovereign militaries once bought thousands of square kilometers, an individual can now purchase as little as 1 to 5 square kilometers. The cost of this data is now governed by 3 clear variables: the spatial resolution, the age of the archive, and the total order area. As this matrix shows, an investor on a $100 budget can now secure 5 square kilometers of archive data at a 30-centimeter resolution. This modular pricing provides the same spatial access to a solo researcher that was previously reserved for large institutions, allowing for low-cost experimentation. Purchasing the imagery is only the first step. The real challenge is processing the complex multispectral data arriving from orbit. There is a common assumption that a user can simply feed a raw GeoTIFF file to a large language model and ask it to count objects. In practice, direct visual classification by AI models has a 0% success rate when identifying subpixel objects in low-resolution imagery. The model cannot identify details that the sensor's physical resolution didn't capture. Advanced agents like Claude 4.6 Sonnet are not utilized as visual classifiers. Instead, they act as orchestrators for the underlying spatial mathematics. These agents bridge the gap by taking a natural language directive and writing the complex Python scripts needed to parse Earth observation data. Modern GEOINT is a deterministic mathematical problem. It is not a matter of image recognition. Google's Gemini 3.1 Pro is designed for this type of complex reasoning. Its 1 million token input window allows it to synthesize entire codebases without truncating the logic. The model integrates with Google Cloud to ingest Alpha Earth embeddings, 64-dimensional vectors that distill petabytes of planetary data into analysis-ready formats. To manipulate this data, the AI writes its scripts using a set of standardized Python libraries. Rasterio is the foundation for reading and writing raster data, allowing the script to extract raw spectral bands from the satellite image. GeoPandas manages vector data, calculating the exact spatial overlap between a property boundary and the satellite pixels. X-Ray manages multidimensional data cubes, making it possible to track historical trends and seasonal anomalies across months of imagery. By commanding these 3 libraries, a single user effectively operates an automated virtual GIS department. Raw satellite data is messy. It arrives distorted by atmospheric light scattering, water vapor, and aerosols. The first task is writing a script that converts top-of-atmosphere radiance into mathematically accurate surface reflectance. The script then applies a cloud masking algorithm, which identifies and nullifies pixels containing thin clouds or shadows that would otherwise skew statistics. All data is then reprojected into a unified coordinate reference system to ensure precise alignment with ground-level maps. Once the data is clean, the AI generates a random forest classification script. This isolates the specific color variance along a highway corridor. The code validates the presence of the separated red, green, and blue bands, confirming the object is moving at speed. By measuring the spatial distance between these bands across the 1.01-second delay, the script calculates the vehicle's exact speed and heading. This rigorous pre-processing is what allowed an investor to turn optical noise into an independently verifiable economic indicator. Deploying generative AI for financial analysis involves a major risk: data hallucination. If an agent fabricates a geographical statistic or an object count, the resulting forecast is worthless. To prevent this, the workflow uses automated reasoning checks. The AI is restricted to generating deterministic Python code, ensuring that all results are calculated by logic rather than probabilistic text generation. Next, we use multi-sensor cross-validation. Findings from optical imagery correlate against structural density data from radar sensors, confirming a visual anomaly has physical mass. Finally, vetted document fencing restricts the AI's context strictly to verified supplier metadata, preventing it from filling data gaps with assumptions. This multi-layered verification is the only way to guarantee analytical integrity in a high-stakes environment. This architecture scales across sectors. It allows a small agricultural firm to predict crop yields by calculating vegetation vigor weeks before the harvest. It translates to monitoring maritime logistics and container throughput at global shipping hubs. The institutional monopoly over physical world intelligence has ended. An individual with a Python script can now observe industrial throughput once reserved for sovereign intelligence agencies. The competitive advantage has moved to those who can bridge remote sensing data with automated AI orchestration. The capacity to independently verify global economic activity from orbit provides a primary source of truth that exists outside of company press releases or official government statistics.